Hello everyone. Today we'll start our video with Kernel of linear transformation. In last video we saw the vector space isomorphism, that is, if T is linear transformation from any vector space U to V, then we can say T is vector space isomorphism if T is 1, 1 and 1, 2. Okay, so for every time T need not be a 1, 1 function. That means if we are talking about the 1, 1 function, suppose if f is a function from A to B, then you can say this f is 1, 1 if for every element of B, that is B1, B2, that is Bn, it has unique preimage in A. Even if this condition satisfies by this f, then we can say this function f is 1, 1 function. But if this suppose this is a vector space U and this is a vector space V, and if we define T is a linear transformation between these two vector spaces, then I already told you that for every time T need not be a 1, 1 function. Okay, so it means suppose if I consider any element V of this capital V, it might have more than one preimage in U. Okay, if this cases arises, then this T cannot be a 1, 1 function. Okay, so suppose UV, suppose, now look at this very carefully. Suppose if I consider U1, U2, suppose UI, okay, are the vectors of this U. Now, if all these vectors maps to the zero vector of V under T, okay, if all this vector, all this U1 UI maps to the zero vector of V under T, then we can say this collection of vectors of U is called the kernel of T. Okay, this means this is a subset of U, and a subset of U such that for every element of subset of U, if it maps to a zero vector of V under T, then we can say this collection of these vectors U1 UI is called the kernel of T. Okay, or you can say null space of U. So in this case we cannot directly claim this is null space, because whenever we are talking about the null space, then it must be satisfied the condition of subspace. Okay, so subspace of which vector space? This, because it is a subset of U only. Okay, now look at the proper definition of kernel of T. Let T from U to V be linear transformation, then the kernel of T is subset of U consisting of all vectors U whose image under T is zero vector of V. That is, kernel of T equal to nt equal to u belongs to capital U, such that t of u equal to 0. So this is the definition of kernel of linear transformation. Now our next task is to show whether this kernel of t is subspace of u or not. To show nt is subspace of u, we have to show the two conditions, that is non-emptiness of this t, that is non-emptiness of nt, and number 2 is for u1, or you can say u comma v belongs to nt, au plus bv it also belongs to nt. If these two conditions satisfies by this nt, then we can say this nt is the subspace of u. Okay, vector space U. So let's proceed the condition number 1. Now this is very easy. Now look at the definition of linear transformation. Moreover, look at the properties of linear transformation. So in last videos we have already saw these properties, that is if t is a linear transformation from u to v, then t of ui equal to vi, and moreover t of 0 vector of u equal to 0 vector of v. So these properties we have already seen in last videos, that is the properties of linear transformation. It means this nt, means u, the collection of this u1 to un, right? So this nt has at least one element, that is 0 element of 0 vector of u, such that t of u is equal to 0 vector of v. T of 0 of u equal to 0 of v. It means it has at least one such element such that t of 0 u equal to this. It means this nt has at least one element such that that element satisfy the definition, and or you can say the condition of the definition of this kernel of t. Okay, so this means zero of u belongs to nt, because we already know t of 0 of u equal to 0 of v. Okay, it means this is the definition of kernel of t only. So by this condition also, this nt has at least 0 element such that t of 0 vector of u equal to 0 vector of v, which implies nt is non-empty, right? Okay, so the first condition is satisfied by this nt. Now we have to show the second condition, that is suppose u comma v belongs to nt. Now we have already picking the two elements of nt, that is u comma v. This means it has a properties such that t of u equal to 0 of v and t of v is equal to 0 of v, because these two are the elements of nt itself. That means we can write t of u equal to 0 of v and t of v equal to 0 of v. Okay, this is small v. Now we have to check whether au plus bv is the element of nt or not. Okay, we have to show. to show AU plus BV is the element of NT or not. For this, suppose AU plus BV is equal to 0 of B. If we show this, okay, if we show this T of AU plus BV equal to 0 of B, then we can say this element is also the element of this NT. Okay, for this, T of AU plus BV can be written as, we already know this T is linear transformation, so by the properties of linear transformation we can directly write AT of U plus BT of B. Now again, look at the definition of TU. So what is the value of TU? From this we can put 0 of V, again B 0 of V. Now you know the scalar multiplication of vectors. From this you can write this or this. This can be written as this, which implies T of AU plus BV is equal to 0 vector of U, which implies this is the element of NT only, because this also satisfies the definition of kernel of T. Thus AU plus BV is the element of NT. Hence, NT is subspace of U. So we proved this kernel of T is subspace of U. Now only we can easily say this kernel of T is null space. Okay, now look at this theorem or this properties of kernel of linear transformation. Suppose if T from U to V be linear transformation, then T is 1 1 if and only if NT equal to 0 vector of, this is 0 vector of, this is 0 vector of U. Okay, so this is if and only if condition, that is double implies condition. So we have to show by taking, first we have to show by taking this is true, and we have to show this, and second is by taking this we have to show this is true. Okay, so from both sides we have to show. Whenever we are talking about the if and only if theorem, then we have to show if we have given P and Q statement, then we have to show P implies Q, and also we have to show Q implies P. Okay, if we have given a if and only if condition, okay, then we have to show this. Now in this case, our P statement is T is 1 1, Q statement is NT equal to 0 vector of U, and first we'll show P implies Q. Suppose T is 1 1, then by taking this statement is true, we'll prove this NT equal to 0 vector. This means kernel of T has only one element, that is 0 vector of U. Okay, proof. We have given we'll show first this, after that we'll show the backward one. Okay, suppose T is 1 1. Okay, we are taking the P statement. Suppose T is 1 1. Now to show what we have to show NT is 0 vector of u. This means, suppose this is u and this is v. Suppose this is linear transformation t. So this is the collection of, suppose u1, u2, un, such that u1 equal to u2 equal to ui equal to 0 vector of u, because it has only one vector, that is u, and this is the kernel of t. It goes to the vector of v. Okay. Now in this case, suppose u is the element of nt. Okay. Now if we are taking any element, arbitrary element u of nt, then if we can able to show this u is also equal to 0 vector of u, then we can say this is true. Okay. Now suppose u belongs to nt, then by the definition of kernel of t, t of u maps to the 0 vector of v. And we also know this is same as this, because this is the property of linear transformation. So at least one element 0 of u such that it maps to 0 of v under t. Okay. Now, which implies t of u equal to, images are equal. Okay. T of 0 comma u. Now look at this. This is the image of u and this is the image of 0 vector u. Now this tu and t of 0 vector of u are the element of, in this case, t of u and t of 0u. So these are the element of v, and these two are the images of u vector and 0 vector of u. And we have already given this t is linear transformation, or we can already assumed this t is linear transformation. So linear transformation is 1 1. Okay. Now if we have given this t is 1 1, by the definition of 1 1 function, if the images of two elements are equal, then the given two elements also equal, or you can say the pre-image of the two images are also same, which implies u equal to 0 vector of u, since t is 1 1. Okay. By this condition, now look at this. In first case, we have taken u is arbitrary element of nt, and we show this u equal to 0 vector of u. So this is for all u belongs to nt. Okay. This implies whenever we are taking any element of nt, then we can get that element is always equal to the 0 vector of u only, which implies nt equal to 0 of u. So the first part is done. Now the second is reversed one. Okay. What is the reverse one? So we have to take the statement first, Q statement. Now what is our Q statement? Suppose nt is equal to 0. Okay. Now we have to show, what we have to show? T is 1 1 function. Okay. We have to show t is 1 1. First we will take any two images of, suppose say u1 and u2. from this vector space V, and if we able to show u1 equal to u2, so which implies u1 is equal to u2, then we can say this t is linear 1 function. Okay, for that, suppose let t of u1 is equal to t of u2. Okay, suppose we are taking this. Now if we can able to show this u1 is equal to u2, then we can say this t is linear. Okay, so from this, t of u1 minus t of u2 is equal to t of u2 minus t of u2. I am taking additive identity of t u2 both side. So t of u1 minus t of u2 is equal to 0 vector of v. So these are the element of v only. That's why I can write this is the element of 0 element of v. So from this, by using the properties of linear transformation, we can directly write t u1 minus u2 is equal to 0 vector of v. Okay, now again look at this. T of u1 minus u2 means, suppose this is also a vector, suppose this is tw vector. Okay, now t of w is equal to 0 vector of v. This implies w is the element of nt. Okay, can we write this? So which implies u1 minus u2 belongs to nt. Now what we have given, nt has only one element, that is 0 of u. So from this we can directly write u1 minus u2 is equal to 0 vector of u by taking the additive identity of u2. u1 is equal to u2. Okay, which implies t is 1 1. So this, now look at this. From this theorem we can directly claim that whenever you have given t is 1 1, okay, then you can directly say the kernel of t has only one element, that is 0. Okay, again when you have given kernel of t has only one element, that is 0 element of u, then you can directly say that linear transformation t is 1 1 function. Okay, so this is the trick. Now next we see the range of linear transformation. Okay, so range of linear transformation. A linear transformation need not be a onto function every time. Okay, so suppose if we have a linear transformation t between two vector space u and v, then this t need not be a onto function every time. Okay, so it means if this t is onto, then in this case for every element of v, okay, for every element of v it has at least one element in u. Okay, so this is the definition of onto function. Suppose v1 v2 vn are the element of v, and if t is onto, then this v1 has at least one element in u, such that t of u, suppose this u1, such that u1 is equal to v1. So it might have t of u2 is equal to v1 also, t of u3 is equal to v1 only, but at least one u1 or one u in u such that t of u is equal to v1. Okay, so in this case, for every element of, for all v belongs to v. Okay, so if this condition arise in this case, then we can say this t is onto function. But every time this t need not be a onto function. Okay, whenever this is onto, in this case, v equals to range of v. Okay, sorry, range of t in this case. Okay, whenever t is onto, then we can directly say this range of t is equal to whole vector space v. Okay, it means range is the subset of v such that it is the collection of images of the element of u. Okay, this collection, suppose it has v1, v2, v3, vn on, this is one collection. Now again it has vn plus 1, vn plus 2, which is not included in this collection. Okay, in this case this function is not onto. Okay, so in this case this is not equal to, this vector space is not equal to range of t, because these two elements are not in this collection. So this collection is called the range of t. Okay, range of t. Okay, now look at the proper definition of range of linear transformation. Let t from u to v be linear transformation, then the image or range of t is the set of all vectors in v that are images on the t of vectors in v. Okay, images on the t of vectors in u. Okay, in this case range of t equal to rt equal to tu such that u belongs to u. So this is the definition which I have already defined in this above figure. So now again in this case also, this range is also subspace of v. Okay, first of all we have seen this range is the subset of v whenever the function or linear transformation t is onto. In this case the range of t is the whole vector space v. Okay, now if we do not have given t is onto, then in this case range of t is a subset of v. Okay, now proper subset of v. Now we have to show whether this range of t is subspace of v or not. Okay, to show the range of t is a subspace of v, we have to show the non-emptiness of range of t, rt, and if we take any two elements of rt, and if the linear combination of the two elements also belongs to the same set rt, then we can say rt is subspace of v. That is, we have to show, number one is non-emptiness. We have to show rt is not equal to 5. Number two is we have to show for u comma, or you can say u comma v belongs to rt, au plus bv it also belongs to rt. Okay, we have to show this. If these two conditions satisfied by this rt, that is range of t, then we can claim this rt is subspace of v. Okay, so our next property is to show rt is subspace of v. Okay, to show rt is subspace of v. Now again, by using the same properties, we can claim the non-emptiness of RT. Okay, we can write 0 of V belongs to RT because we know the properties of linear transformation. 0 of V is one of the image of 0 of U in U. Okay, so by this property we can say at least this 0 of V belongs to RT, which implies RT is not equal to phi. Okay, now the second condition is, suppose V1 comma V2 belongs to RT. Okay, now we have to show A of V1 plus B of V2 it also belongs to RT. Okay, so we have already said that this V1 and V2 are the element of RT. This means this is the some image of, suppose this is the image of U1. We are considering, suppose this V1 is the image of U1 and this V2 is the image of U2 under T. In this case, V1 can be the image of U1 and suppose V2 is the image of U2. Okay, now what we have to show, we have to show this element is also image of, suppose this is W. Okay, suppose you can say, suppose this is V3. So, look at this. Suppose we are considering A V1 plus B V2 is equal to V3. Then this V3, we have to show this V3 is also the image of U3 in U. Okay, so in this case, A of V1 plus B of V2 can be written as, what is the value of A V1? A T of U1 plus B T of U2. Okay, and we already know this T is linear by the using the properties of linear transformation. We can directly write this as T AU1 plus B U2. Now again look at this. This is same as okay, this is AB1 plus BB2. Now this is, suppose this is V3 and this is U3. Now we can say this V3 is also the image of U3, with this U3 is the element of U. Okay, so which implies V3 belongs to RT. That means what is the value of V3? A V1 plus B V2 is also the element of RT. Okay, now which implies RT is subspace of V. Okay, so we show that we proved that this RT is also the subspace of V. Now up to this, what we have seen, kernel of T, that is null NT, is the subspace of U, and RT is the subspace of B. Okay, so these two are the very interesting topic in this linear transformation. Now for today we'll see one theorem. After that we'll stop there. Okay, so look at the theorem. If T from V to V is linear operator, okay, in this case we are considering this T from same vector space V to vector space V. In this case we can say this linear transformation as linear operator. Okay, so if T from V to V is linear operator, then the following statement are equivalent. Number one is intersection of RT and NT equal to 0 vector. Number 2 is if T of TV equal to 0, which implies TV equal to 0. Suppose this is P statement and this is Q statement. This is same as if and only if condition, because we have already told that we have already defined this two. We have to show you have to show these two statement are equivalent. That means we have to show P implies Q and Q implies P. Okay, so from both sides we have to show. First case, we have to take, suppose this P is true, then we have to show this Q is also true. Okay, and next, suppose if we take this Q is true, then we have to prove this P is also true. Okay, so first we'll show 1 implies 2. It means I'm taking the first P statement is true. By taking this P, I have to show this Q statement is also true. So what we have given in P statement, RT intersection of RT and NT is 0 vector. Now I have to show if T of TV equal to 0, then which implies T of V equal to 0. Okay, I have to show this. For T of TV equal to 0, we have to show T of V equal to 0. Okay, and we have given this condition. Okay, this statement we have given. By taking this statement as true, I have to show this T of V equal to 0 if T of TV equal to 0 vector. Okay, now for this, T of TV is equal to 0. This means, okay, we have already given this is true. By taking this condition, I can claim this TV is an element of what? Kernel of T, because we know the definition of kernel of T. If I take any element U from this U, in this case, if I take any element U from this capital U such that T of U is equal to 0 of V, then we can say this element belongs to the kernel of this T. Okay, so this implies T of TV is equal to 0 vector. These are the 0 vector of V, which implies TV belongs to NT. Okay, so TV belongs to NT. Now again, this TV is image of some element of U. Okay, this TV is the image of some element of U, because we know, suppose this is if I take any TV element of this implies this has some element U such that T of, okay, this is some element such that T of V is equal to U. Okay, fine. Now in this case, TV it also belongs to RT. Okay, now which implies TV belongs to NT and TV is also belongs to RT. This implies TV belongs to the intersection of RT and NT. Okay, because TV belongs to both the sets, which implies, and what is the value of TV? What is the value of this intersection of RT and NT? Because we have to show this TV equal to 0. Okay, P is equal to 0 because the intersection of this RT is zero vector. Okay, so the first condition we have proved. Now the second one is 2 implies 1. Okay, now we have to take the Q statement is true. After taking that Q statement is true, we have to show the P statement is also true. Okay, now if T of TV is equal to 0 implies T of V is equal to 0, V belongs to V. To show, what we have to show, intersection of RT and NT is equal to 0 vector. We have to show this. Now let U belongs to RT intersection NT. Okay, suppose if I able to show this this U is equal to 0, then I can say this is true. Okay, I am taking this U as arbitrary element of the intersection of RT and NT, and if I able to show this U is 0, then my work will be done. Okay, now since this U belongs to the intersection of RT and NT, which implies U belongs to RT and U belongs to NT. Okay, since U belongs to RT means this U is some element. Okay, this U is the sum image of U of U, such that in this case, now don't confuse, in this case U is also equal to V. Okay, because we are in linear operator. Okay, in this case this U is also a V. Okay, that is why T of V is possible. Okay, now in this case, suppose we have already claimed this U belongs to RT. This means U is some element under T V of V. Okay, so again what we have given, so U belongs to NT. From this statement I can say T of U is equal to 0 of V. In this case I can write 0 because 0 only, because this is the whenever we are talking about the 0 of V, 0 of U, in this case this is the 0 vector of U, sorry V, and this is the 0 vector of V. In this case U, in this case U equal to V, so I can directly write 0 vector. Okay, so from this statement T of V is equal to 0, because this is the kernel of T. By the definition of kernel of T, I can write this. Okay, now thus I can write T of U is equal to 0 vector. Okay, so from this T of U is equal to T of, what is the value of U? T of T V. So from this, and what is the value of TU? 0 vector is equal to T of T V, which implies T of V is equal to 0 vector. Thus the theorem is proved. Okay, so 2 implies 1 is quite easy than 1 implies 2. Okay, so for today we'll stepping here. From next video, in next video we'll start with the fundamental theorem of vector space homomorphism. Okay.